Hello, good evening everyone. So today I will be conducting the week 6 of the live sessions for the course of Computational Fluid Dynamics. So uh, start from where we left off in the previous week. So we were just about to discuss the unsteady heat equation, and how we can solve that using finite volume discretization. So mm, we like take up this question to further elaborate that point. So if we have an integral uh, which takes this time integral form, then how are we going to pursue it? We already know, in the finite volume method, uh, we use a weighted integral approach where the weighting function is 1. So suppose we have the like a heat equation, let's say ddx 3 dt dx plus s, this is equal to 0. So what we do is integrate with respect to x over the whole domain and set it to 0. So this is exactly like taking a weighting function of 1. Now what will happen if we have an unsteady equation? Let's say we have an unsteady equation where there is no source term. Then we will do the same thing, but not only integrate with respect to x, but also we will integrate with respect to time. And like we have done in steady state equations, we have divided our domain, spatial domain, into different finite volumes. Here also we will discretize time into finite discretizations of length, let's say delta t, as we have mentioned. So once we do that, it becomes very essential for us to, like we did in the spatial coordinates, to have a profile assumption of t with respect to time. So that's where this expression comes in. So you can see in this expression, what we have done is basically represent this time in terms of this temperature, in terms of temperature at time t and temperature at t plus delta t. And we have used this factor f in such a way that it represents the way, the relative importance of the temperature at time t and temperature at time t plus delta t. Depending on the values of f, we would either uh, focus more on the uh, previous time step than the next time step, and vice versa. So if f is equal to 0, if f equal to 0, if we put f equal to 0 here, the second term vanishes. The second term vanishes, and we are left with, in this case, 0 t, t plus delta t, t dt. This is simply equal to t times delta. So this is completely dependent on the previous time step. So this is called the explicit scheme, where all the integrals of temperature are taken to at the previous time step. So why this is explicit? Because in while using this scheme, we often encounter that the next time step is evaluated solely based on all the values from previous time step. And instead of having coupled equations for each and every spatial domain, we end up getting single equations for each particular control volume. So thus this is the explicit scheme. F is equal to 1. If you put f is equal to 1 here, Similarly, we see that temperature at time t, this term vanishes. And what we are left with here is t at t plus delta t. And delta t. So all the importance here is in the next time step. So this is an implicit scheme, which is basically the opposite of this. Here, all the values will depend on the next time step. So you will get a coupled set of equations when we are trying to calculate the temperature at the next time step. Crank-Nicolson scheme is somewhere in between these two, and there we use f is equal to 0.5 in this particular scheme. And this is neither an explicit nor this is in between this explicit and implicit scheme, and like equal importance is given to T at temperature at T and temperature at T plus delta T. So this is not correct. We use f is equal to 0.5 for practical. So among these following statements, which one would be correct? So 1 and 2 are correct in this case. So in this, the third case, we should have f is equal to 0.5. So this is basically what we are when we talk about unsteady equations. Like this is these are the basic schemes that we should keep in mind. So let us quickly have a look as well. So let's say we have an equation here, rho Cp del T is equal to del x k del T del. Notice I am not writing d anymore. I am writing the partial differential sign because there are two independent variables, T and x. So temperature is dependent on x as well as T. So in this case, what would happen? We would do, as we previously like just now discussed, we would integrate this whole equation with respect to x and with respect to t. So let's take the first term and see what does that bring us to. Rho Cp del T del T. So let's first differentiate with respect to t, and we can always interchange this particular thing. So when we are integrating with t, we would go from t plus t plus delta. And x we will do in like control volume setup. This is a control volume setup. So we will do it likewise. So I'll put Cv here, and whatever are the limits that we need to put, we will put. So this would bring us, since this partial differential is there, we will simply integrate this rho Cp, and this becomes T at T plus delta T. So let's call that T1, and at T, let's call that T0. Now we are integrating over a control volume, and like uh, just to recall how the control volume looks in like finite volume methods, we have a grid point which is at the centroid of a control volume, and we have a point towards the east, point towards the west, and these are the west and east boundaries. And what we do for evaluating each integral, we assume a profile assumption. We assume a profile for the temperature in the control volume. So we discussed piecewise linear profile assumptions when we were discussing the conduction equation with a source term. So there, that particular profile assumption was beneficial for us to evaluate uh, evaluate things at that time. We also have discussed like constant profile assumptions when we were discussing source term when source term dependence with temperature. So there we had used constant profile assumption. Here also you will use constant profile assumption because that will suit us. Like here we really don't need any piecewise assumption. We want to focus on a particular value. So we will do a constant assumption here. So we would write this as Cp. If this is a constant temperature assumption, then this is T1 at I minus T0 at I delta x. So T dt integration T dx becomes T delta x because we have assumed the constant profile. Alright, let's look at the second term as well quickly. The right hand side term. What would happen when we integrate it with respect to T and x? And in this case, what we would do, we would first integrate with respect to x because that would help us simplify the equation or calculation. And d at the end. This is t plus delta. What happens here? Again, here we will put del del x dx. So this will be simply k dt dx at the two boundaries, east and west side. Here we will again like use that piecewise linear profile assumption so that we get a particular slope for each term. We will do that. So this becomes k east. Let's put this point p. It's not dvi. So this is T minus T delta x minus kW Tp minus Tw divided by delta x. So I am assuming this delta x to be constant. We can not as well. We can do the most generic case. Now, when we integrate this time integral, we would come across terms like Te dt integration Tp dt integration Tw. For that, we will use these things that we have seen in the previous question. So now, if we evaluate this, all these terms will be 1 minus f. So 1 minus f t plus f t plus f. So f, where f will vary from 0 to 1, and depending on what is the value of f, the scheme will be defined as such. So if f is 0, the if f is 0, then this integral depends only on the previous time step and thus becomes an explicit scheme. If f is 1, then it becomes an implicit. Alright, so let's look at another question. Consider 1D unsteady heat conduction through a slab of thickness 10 centimeter. Thermal conductivity is given, thermal capacity is given. If the domain is divided into 20 equal control volumes and the Crank-Nicolson scheme is employed, the maximum size of time step in second that can be used. So how would we do that? What is required? Which knowledge is required for this? The question that is asked is regarding maximum time step size. So that would come from the stability analysis of these particular equations. So note we were like developing a scheme uh, from this unsteady conduction equation, and uh, after simplification, this would result in our generic form plus b. So if here we had discussed previously, whatever the sign of AP, the same sign should be of AW and AE, because if TW increases, we must expect that TP should also increase, and if TE increases, we must expect TP should also increase. It should not happen that they are uh, like inversely related. We cannot expect that TE would increase and then that would result in a fall of TP. That is unphysical. So if the points are close to each other, if one temperature for one point temperature rises, the other point's temperature should also rise. But here in this case, there will be another term which will be AP0, TP0. What is this AP0, TP0? These are for the temperature of the previous time step. So, like taking from the same logic, if previous time step temperature is high, the next time step temperature should also be high. So, this should be positively correlated, right? It cannot be inversely correlated such that the temperature on previous step, if increases, the next temperature would decrease. That cannot happen. So AP0 will also follow the same rule we had applied for AE and AW. And while applying this, we come across certain rules for different this value of F. Hmm, that needs to be followed so that AP0 is positive. And what are these rules? For explicit scheme, we have alpha delta t divided by delta x square. This should be less than equal to half. For Crank-Nicolson scheme, alpha delta t by delta x square, this should be less than 1. So this is a relaxed criteria compared to explicit scheme. Whereas implicit scheme is unconditionally stable. So unconditionally, we will have the same sign of AP0. So for implicit scheme, we do not need to worry about this kind of a values. Okay. So what is this alpha delta t by delta x square? This is what is this called? This is called as a Fourier number. Fourier number. So Fourier number is generally like, even if it is a time scale and a length scale of some different sort, it is also called a Fourier number. Here in this case also, this is referred to as a Fourier number. Uh, so here it is said that we are using a Frank-Nicolson scheme. So we would use the this particular inequality. So we have to first calculate alpha. What is alpha? Alpha will be K by rho C. So can you please tell me the value of alpha? So these are all already written in uh, the SI units. So simply put the value 100 divided by 10 to the power 6. So that gives me 10 to the power minus 4. It will be of a certain unit. You can calculate the unit. But I am working on SI units, so I will not bother right now. So 10 to the power minus 4 into delta t by delta x square. This should be less than equal to 1. What is delta x? So slab of thickness 10 centimeter, and this is divided into 20 equal domains. So delta x is delta x will be so 0.1 meters divided by 20. This is delta x. So my delta t will be less than equal to 0.01 divided by 400 into 10 to the power 4, which is equal to 0.25. You can check the calculations if the calculations are not incorrect in order. So this gives me a value of 0.25. So this is how we will estimate the value of the maximum size of spine step from the stability criteria. Okay, let's move to the next question. So suppose FTCS scheme is employed for discretizing 1D transient heat conduction equation. If it is desired to attain second order accuracy in time and fourth order accuracy in space, what is the value of self-Fourier number that must be used? So for this, we need to know a few things. FTCS. What is FTCS? So till now we were discussing in the unsteady problem with finite volume. We have shifted back to finite difference in this case. So finite difference method. If I hope you remember this. So this is where we discretize the Taylor series evaluated the Taylor series expansions and truncated up to a certain number of terms, from where we develop uh, expressions for the derivatives and use those expressions to formulate numerical schemes. So FTCS is nothing but forward in time and central in space. So this is very self-explanatory. So what we would do, uh, so let's say our time we denote by the superscript. So something like this would denote my del t, and central in space, let's say del square t del x square. How this would be done? This would be simply, all right. So this is how we would represent the things. So, so 1D transient heat equation would look like this: del del t equal to alpha del square t del. So what will be the order of accuracy for this? So this with plus delta t term, and this would involve plus delta square. But here they are asking if it is desired to attain second order accuracy in time. Second order accuracy in time is required, and fourth order accuracy in space is required. Then what is the self-Fourier number? So for second order accuracy in time, what we would need to do is we would need to make the next term vanish. So what is the next term? The next term would be del square t del t square multiplied by delta t. So we need to check for the coefficient here. Uh, so it can be done. So let's for once write down the expression of the Taylor series expansion. That is the best thing that we can do. So let's say n plus 1 is there. This is equal to Pn plus del t del t delta t. So this is what is used. Plus it will be half del square t del square delta t square. So up to here is essential for us because we need to make this term 0 so that the accuracy burden of accuracy shifts to the next term, right? So here in this case we would have half del square t del t square delta t, because we have divided a delta t in this whole equation to obtain what we have obtained right now. All right. So same thing if we do for the spatial term. What we would get. So here we have to do it for two terms. So Ti plus 1. So this is Ti plus del T del x delta x. So this will cancel out, plus half del square T del x square This we are evaluating, and this also we expect to cancel out. Del square del q t del x to the power, sorry, delta x to the power 4. So this much we require. So if I want to find out I minus 1 terms, then this will be negative, this is positive. Uh, this term is definitely positive, this is negative, and this is positive. So if we cancel out, uh, this term cancels out, and this term cancels out, while these two terms add. So what we are left with here is 1 by 12 del to the power 4t by del x to the power 4 delta x to the power 4. And this is what is important to us, because this is what would determine that the burden of accuracy shifts to the next term. So let's evaluate what we have got. So what we have got is half del square t del t square delta t, and we have minus del square t del x to the power 4 delta x square, and there will be an alpha here. The alpha will be there because the special term has an alpha. So far whatever we have got has led us down to this particular term. And if this particular term is 0, then we obtain our required second order and fourth order accuracy. So, but we have like time derivative here and space derivative there. So that's a problem, a little bit of problem. So let's try to use this governing equation to try to find expressions for this. So for time derivative, this should be pretty straightforward. This is alpha, this will be del q t, del t, del x square. But that also does not solve our problem much. We need to do a 4 as well. So that also we can do. So if we take derivative with respect to x 2 times, then we will obtain an expression such as this. And now this solves our problem because we have the same expressions here. So if I like substitute this, what we get is simply so alphas I need to alpha will be here. So alpha delta t by 2 minus delta x square by 12. This should be equal to 0. That gives us alpha delta t divided by delta x square, which should be equal to 1 by 6. And this is the expression that was asked. So this is the Fourier number, and this should be 1 by 6. Okay. So I have done a lot of calculations in this page. So hopefully this is like clear to you. If not, please like ask in the next class. Okay. Or you can ask now also. You can ask anytime basically. All right. So let's move to the next question. The next question is about Lax equivalence theorem, and we need to know the Lax equivalence theorem if we want to answer this particular question. So what is Lax equivalence theorem? So it deals with the convergence of a particular problem. So it states that, let's go through the statement and we will find this. It states that linear problems, stability and consistency implies convergence. And this is exactly what it states. So for linear problems, stability and consistency will imply convergence. That is Lax equivalence. Uh, what is the second point? Lax equivalence theorem states that for nonlinear problems, stability and consistency implies convergence. That is, this is not true. This is not true. It only is applicable for linear problems. Okay. What is the next? For a linear problem, grid independence and time step independence tests must be performed. Uh, this statement is not required if lax is like uh, satisfied. If stability and consistency is satisfied, we do not really need to perform any grid independence or time step independence test for linear problems. However, for non-linear problems, we need. So 4 is also correct. So 1 and 4 in this case are correct statements. So B is the correct statement. Alright. We move to the next question. So please try attempting this one, and we can restart after a 5 minutes break.
Sir,
Yes, please.
the audio is not here, sir. You stopped or
No, yeah, I was. Uh, I will restart right now. I
okay, okay, okay,
uh,
okay, sir, okay.
I said that for a break. No, I will
Okay,
restart right
okay, it's okay. It's okay, it's okay, sir. Okay, sir.
now.
Okay,
Okay. So let's start with this particular. So four statements are given, and we have to judge which statements are true and which statements are false. Okay. So the first statement is CTCS scheme. So what is CTCS? CTCS is central in time and central in space, and FTCS is forward in time and central in space. So if the CTCS has a higher order or accuracy in space and time as compared to FTCS. This is not necessarily true, uh, and we will see why. So order accuracy, higher order accuracy, uh, like generally your in space you have the central difference key, and that will provide you the higher order of accuracy. So at least in space, the CTCS does not have a higher accuracy order. The The second statement is also not true. It does not have a lower order accuracy as in space as well, because CTCS, they both have are the central schemes, and they have the equal order of accuracy. Finally, we have CTCS scheme is unconditionally stable uh, when compared to conditional stability of FTCS scheme, and CTCS is unconditionally unstable as compared to conditional stability of FTCS scheme. So the fourth statement is here correct. Hmm. So CTCS scheme, as we would look in the classes, it has an unconditional instability. So this CTCS scheme is not a stable scheme. Hmm. So how you will judge the stability of schemes? So stability of schemes is generally judged by like checking whether or like the 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 error, if the error is approximated as, let's suppose t minus some t star, which is an approximate solution. This is approximate solution, and both of them will satisfy the our like the schemes, the numerical schemes that we have proposed. And what is basically is done is this error is represented using a Fourier series expansion. So any function can be like written in terms of Fourier series expansion. So some amplitude is some time amplitude and a bounded spatial term. Why bounded? Because like spatial term, physically it will not explode dramatically. So this is bounded, and its amplitude is kept in check by this AJ term. So this is basically like sine function sine and cosine functions. So this is e to the power I kx. So this will be some sine function, and this j is actually the uh, this z is actually the time function, and this is represented as a e to the power at. So now what is generally done is we take any one term of this error function and say that this is an arbitrary term and put it inside the scheme and see if e to the power a delta t this this is like it means increasing rapidly or not. So if this is very high, this is the magnitude of this is greater than one, then we would say that this is unstable. If this is less than equal to one, then we will say this is stable. If it is less than equal to one, then we will say this is stable. So we
Sir,
can
one more
like
doubt, sir.
yes,
Sir,
definitely yes.
sir, can you explain that conditional and unconditional any criteria, sir? For
Yes, when we are like doing the stability analysis, uh, if we for certain terms we have certain we develop certain conditions. Like for example, say alpha delta t by delta x square. This is less than equal to half, and this is what we would get for our FTCS. And
I see.
we also got that for like our explicit scheme in our finite volume methods. So this is stable provided this. So if this is true, then we have our stability. So this is the
Okay, sir.
condition which
Okay,
makes it
sir.
stable.
Uh,
Conditional stable. And if no such condition exists, it is like unstable without any condition. So no condition can make it stable. Then it is
okay,
unconditionally unstable. So that is the
okay,
CTC system. The
okay,
CTC
sir. Okay,
scheme unconditionally unstable. Okay. So 1 and 4 here in this case is the correct statement. All right. So we go to the so sorry, one was not okay. So only 4 was the correct. Yes, because we discussed like this is does not have a higher order accuracy. All right. So CTCS scheme is unconditionally unstable, but why we use central difference? Central difference is generally used for this like higher order accuracy, but we see that this is unconditionally unstable, so we cannot use it. So there is another attempt that is generally made, which is called as the Dufour-Frankel. So Dufour-Frankel scheme. So what is done in Dufour-Frankel? Dufour-Frankel, this is replaced by average of uh, previous and the current next time step. So this is the correct one. So like in general, in such schemes, what we have is Tn plus one minus Tn minus one we will have. So this is central in time. So 2 delta x, and we will have this alpha. Sorry, delta x now. This is delta t, and we have delta x square n I plus 1 plus I minus 1 minus 2. So this is our CTCS scheme. Central in time, central in space. This is CTCS scheme. So here what we do is this term is replaced by an average of previous time step and the next time step. What does this make? This will make this as unconditionally stable. Unconditionally stable. So here, if we do the stability analysis, we will see that without any condition only, this will always come to be a stable scheme. So this is the first option is correct. So I plus one term is not replaced, and yes, we do not use the spatial averaging. We use the temporal averaging. So this n plus one, the superscript always denotes the time. So that is average. All right, let's move to the next one. So yes, this particular scheme is we just now mentioned that this is unconditionally stable. So this is stable for every like without any condition. So no condition is required. It is always stable. However, this has problem with consistency. So this is inconsistent. So this is inconsistent in nature. Uh, what is inconsistent? So consistency is basically like if we have our the scheme that we have, we can always write it in terms of our Taylor series expansions, right? So let's say del this we are like writing in terms of some central difference scheme. So plus it will have some delta t square order of error. Now, if delta t tends to 0, what would happen? This order will tend, this error terms, the truncation error terms, this will go to 0. However, if at when delta t tends to 0, this truncation error does not go to 0, this makes it inconsistent. So, if truncation error vanishes when delta t and delta x tend to 0, then it is consistent. Consistent. Otherwise, it is inconsistent. So Rufo-Frankel scheme, despite being unconditionally stable, we can show that this actually is an inconsistent scheme. How will you show that? So here we just wrote down the scheme, and if we try to convert this in terms of like the in terms of Taylor series expansions, and then like the terms will cancel out, and you would be left with the truncation error terms. And those truncation error terms, you would see that they would not vanish to 0 if you make the step size 0. So you can do that exercise. You can put Taylor series expansions in place of each of these terms. In place of each of these terms, you have to put Taylor series expansion and see whether this is consistent or not. So, so the answer will be C, inconsistent and unconditionally stable. All right. So far what we have discussed is the unsteady part, the unsteady 1D equations. There's a lot of things are here, especially the things that are important is stability analysis, and means the different types of schemes that are there, which one is stable and which one is conditionally stable, and what is the condition that arises from its like stability criteria. So those things are important. So we have completed that part, and now we will move to uh, like solving equations, system of linear equations. We'll just do a brief introduction to this part today, and we will have our next live session and in the usual time again on Tuesday. So this week I my health was bad, so we had to shift it to Saturday. We will again resume the like normal timing from the next week.
Okay, sir.
Okay, let's do this question. So consider a system of linear algebraic non-homogeneous equations. So linear algebraic non-homogeneous equations, what does this mean? So linear equations, you will have linear expressions. So let's say a1 x1 plus a2 x2. Let's say n variable equation. So a n xn. So this is linear. Hmm. This will follow all rules of linearity. So if this is equal to 0, then this is a homogeneous equation. However, we put some coefficient here, v1. So now this is an inhomogeneous, non-homogeneous linear algebraic equation. But there are n variables, only one equation, so we cannot solve this. So we need n equations. So let's put one here in these coefficients, and we have our next equation like this. And we have like n equations, and the last equation would be like this. Now this whole thing, this can be written as a matrix with all these A. So all A's can be stored here, and this is X, X1, X2. So you can see like this matrix can be multiplied with this, and you will get this particular set of equations, and this is all the B stuff can. So actually, whatever scheme we are using, we are always whether finite volume we are using, finite element method, or finite difference method, we always try to obtain linear equations. Now, after we obtain a linear equation, we can always like arrange it in this particular form. So Ax is equal to B. So this is a matrix equation. So this is our main aim for every numerical method we are doing, because it is easier to solve algebraic equation than to solve differential equation. So differential equation we convert it to algebraic equation, and now we will see how to solve this algebraic equation. So basically we have to do this A inverse B. So A inverse is to finding A inverse is the main challenge. So that's what we are now looking forward to. So here is it is here it is saying something about ranks of this matrix. So RC is the rank of the coefficient matrix. What is the coefficient matrix? Here in this case, A is coefficient matrix. So rank of A is given as RC. What is rank? So rank is basically rank is how many independent row vectors are there. That is the main definition of rank. So row vectors are basically like each row is a row vector, and how many independent number of them are there, that is the measure of rank. But how can you like say in more like crude way? Uh, we have different row operations. Like we can We have three different kinds of row operations that we can do while like solving linear equations. One is we can exchange two rows, so RAB, so RA becomes RB and RB becomes RA. So that we can do, or we can choose some RA and that can become some RA plus some constant, let's say some C into RB. That can happen, or what else? We can simply like multiply something to the whole row. That also we can. So we can interchange rows, we can like add or subtract from any other row. So these row operations we can do. So after these row operations, if we convert this A matrix into a upper diagonal matrix. So so this diagonal is there. So below all these elements will be 0. So all these elements are 0, and in this upper diagonal only the non-zero elements are there. So here if we count the number of non-zero rows, so the number of non-zero rows, that will give me the rank. That is how to find the rank. So what is exactly it is giving? It is giving number of independent row vectors. We will see another example of this. And then I think like it might be more clear if it is not now. So RC is the rank of coefficient matrix. So coefficient matrix is A, that is RC, and RA is the rank of augmented matrix. So what is augmented matrix? Augmented matrix is basically A, and you add another column and write down the B vector. So A slash B. So rank of A slash B is the augmented matrix. This is equal to R. And n is the number of variables, which we have already denoted by n. So, it is asking when the solution is unique or when it is inconsistent. So, solution is unique when RC is equal to RA is equal to n. Is that correct? So this is correct. This is basically what we are looking for. So we want a unique solution, and if we want a unique solution, we must have the rank of the coefficient matrix equal to rank of augmented matrix, which is equal to the number of variables. If this is the case, we can find unique values of each and every variable. So x1, x2, to xn, each variable we will get unique values. So this is correct. System is inconsistent when RC is equal to RA, and but this is less than n. So if RC is equal to RA, that means the number of like independent rows, that is not changing when you are adding the like the last column. So that would mean that the system is still consistent. We will still get a solution, but the solution might not be unique. There might be a number of a solution, infinitely many solutions that we get. So, but the system is not inconsistent. So this statement is incorrect. Okay. So what else is there? There exists infinite number of solutions when RC is not equal to R. So this is also not correct, because if RC is not equal to R, we get inconsistent system. Then we do not get any solution. So no solution when RC not equal to RA. Infinite solution when RC is equal to RA, but this is less than n, and exactly one unique solution when RC equal to RA equal to N. So these two statements are correct. And the first one is these two statements are wrong, and the first one is correct. So this is the correct answer. Okay. All right. We have a system of linear equations here. So here the unknown variables are A, B, and C. So my x vector, this is A, B, C. What is my coefficient matrix here? So I will write down the first equation. So A is 1, minus 3, and 1. So notice how I am writing it down. I am taking each coefficient and writing it here. So this is minus 1, 2, minus 5. This is 5, minus 13, plus 30. And I have the column vector. So this is 4, 3, 8. So which of the following are correct? That is asked. So let's do one thing. Let's find out the rank. So if I want to find out the rank of A, we would take the augmented matrix itself, and augmented matrix, if we like see only this part, then we will get the rank of A. If we see the whole part, then we will get the rank of all of them. So 1 minus 3, 1, 4, minus 1, 2, minus 5, 3, 8, 13, minus 13, 5. So let's first make these two rows Z. So this first one, if we make it 0, if I make it 0, I will simply add the first row to the second row and replace the second row. So I will like go on replacing each term, because otherwise it like I will run out of space very soon. So this is minus 1. This becomes 0. So that's what we are doing. That's what I was adding. So these terms I can see from here, so I can erase this. So minus 3 and 2, this will become minus 1. 1 minus 5 will give me minus 4. And 4 plus 3 will give me 7. Okay, so I have made this 0. I have to make this 0 as well. So this 5 will be 0. So let me just like erase this last row as well. I can see it from here. So I can erase this. What am I doing? I am subtracting the first row, multiplying it with 5 and subtracting with the third row. So I get 0 in the first column, and that is my objective, is to make this particular element 0. So okay, now this I have to multiply with minus 5, and I have added here. So minus 5, if I multiply, this gives me 15. 15 I add here, so I get 2. Again here minus 5, so minus 5 if I add here, I get 8. Okay, here again minus 5 I have to multiply, so that gives me minus 20. If I add it here, I get minus 12. All right, so I have done this. So next row operation, I will like write the whole thing down. I don't have to change anything in the first row. That stays as it is. The second row also I need not change anything because I have already made the first term 0. However, for the third row, what I will do, I will simply multiply 2 to the second row and add it. So, so that this particular term becomes 0. So I will just multiply 2 and add it. Multiply 2 and add, this also becomes 0. Multiply 2 and add, this becomes 2. So now I can like try to find out what is the rank. So I have obtained my this upper diagonal matrix. So what is my rank of coefficient matrix? So how many non-zero rows are there? One, two. But the third row, you see, this element is also zero. This I have not made a zero intentionally, but by byproduct, this element has become zero. So this will be counted. RC is 2. What is RA? Augmented matrix. Uh, Here, this row can be counted as a non-zero row because the last term is non-zero. So this becomes RA is equal to 3. So what can we conclude from there? We can conclude that the system of equations is inconsistent, right? We have RC not equal to RA. So the system of equations are inconsistent. This is the fact. All right. So this is the amount that I had to discuss today, so that we do not lose out on much. Uh, Next we will continue on our usual time on Tuesday. If you have any questions, please feel free to ask.
Okay, okay, sir. Nothing, sir.
Okay.
Okay,
Thank
sir.
you for joining.
Thank you, sir. Okay.